Hi guys. Hey, today we're going to be working on evaluating logarithms, and we're going to be working on the homework will be worksheet ELF-3. So today is March 19th, okay? And I want to talk today a little bit before we get into this about the number E. There's a lot of different constants out there. One of them that you learned from geometry, and maybe even earlier than that, probably in elementary school, is the number pi, which is defined as the circumference, the length of the circumference around the circle, divided by the diameter. Well, there's another number out there that we learned in higher math, in advanced math classes, and it's the number E. And what we're going to do is we're going to look at what happens as n gets really, really big. So like n goes to infinity. So we're going to make n be 10, 100, 1,000, and so on. And at the same time, we're going to look and see what happens as 1 plus 1 over n raised to the n power. What happens to that? And you're going to see that this is going to approach a constant that we call the number E. So we're going to go to our graphing calculator. I know not everybody has one, but you don't really need the graphing calculator to do the homework. Okay, it's just to explore this, and you can just watch and see how it's done. Okay, so we're going to go to the graphing calculator right now. On our calculator from our home screen, we press y equals, and then we enter a left parenthesis, and then 1 plus, then we need the fraction bar, and 1 over x, and then close the parenthesis and then raise that to the x power. And we're going to take a look and see what happens when x gets larger and larger and larger and larger. Okay, so this denominator is going to get really big, okay, and that's going to make this 1 over a really big number from last unit. We know this is going to get closer and closer to being 0, okay, and then 1 plus 0. And then this is going to get really, really big. Okay, so what happens when that takes into account? So we're going to look at the table, and we're going to start entering numbers like 10. We're going to make x go to infinity. So 10, 100, 1,000, 10,000. And you start looking at this, and okay, so right, these two, all of a sudden it start to be two decimal places the same, right? Both the tenths and the hundredths place are the same. And so that was 10,000, so let's put in 100,000. And now we're getting three decimal places the same. And so that was 100,000, so let's go 1 million. And now all four decimal places. Now, are all four decimal places really the same? So we can go on top of them. And this one is 2.718268 right here. And if we go down, 280. So they are different, right? So let's go a couple more. Let's go. This was 1 million. So now let's put in 10 million. So 10 followed by 3 zeros and 3 more zeros. And I put too many zeros in there. 1, 2, 3, 4, 5, 6. There we go. And still, it's getting closer and closer and closer. So 2.71828. 280, so a little bit different, right? Just slightly, barely different, okay? So this is what's happening is if we continue to do this and get larger and larger and larger and let x go to infinity, this is going to approach the number E. Okay, guys, so let's take a look at this, and we're going to record some of this. So when n is 10, okay, 1 plus 1 over n raised to the n power becomes 2.59374246. And then when n is 100, what we got was 2.704 813 829. And then when n is 1,000, then we got 2.7169 239 32. And then 10,000, and 2.718 1459 27, and then 100,000, and it's 2.718 268 237, and then finally 1 million. Let's take a look at that. So when n is 1 million, it's going to come out to be 2.718 280 469, and I'm going to go out even further, 3193. Okay, so we're taking the limit as n goes to infinity, so we can write this. This is all from last unit. So the limit is n goes to infinity. This is the right n behavior of this, okay, and this would be 1 plus 1 over n raised to the n power. That is defined as this number e, which is approximately 2.718 281828. And this number is like pi, where it never repeats and it never terminates. So this number keeps going on and on. There's no pattern to these numbers at all. They proved that. Okay, this number is really important for higher level mathematics. We use it a lot. It makes formulas in calculus much easier, and you won't see that till next year when you take calculus. Okay, but this number e, pretty important. Okay, all right. So the graph of this, if you look at this graph of 1 plus 1 over n versus n, okay, you look at this graph, okay, and you can see it's going up, and then it's flattening out over here, okay? Now this is only going to 10, and this is going to 100, but you see how it really flattens out, and there's a horizontal asymptote here, okay? And I'm going to get a ruler out, and what happens is, if we extend this, right, this is the horizontal asymptote that we've been talking about, okay? And this turns out to be the number e, okay? All right, so with that said, there's two special types of logarithms, okay? There's what's called the common logarithm, and that's when it's base 10. And we use this because our number system is base 10, okay? So what you're gonna see is log with the little base 10 of x. Now, when you don't see a base, what that automatically means is that it's 10, okay? There's another type of logarithm that's called the natural logarithm, or logarithm natural, okay? That's why we're gonna use the symbol ln for logarithm natural, okay? It's actually log base e. It's this number that we just discovered, okay? It's base e, okay? So when you see ln, you automatically know, and it's assumed that we all know this, that the base for this logarithm is e, okay? So now what we want to do is evaluate logarithms. So what I mean by that is it's going to be similar to like taking the square root. Like the square root of 9 is 3. Like you know what that is, okay? So how do we figure these out for logarithms, okay? So if you look at this first one, okay, this log of 100, what is the value of that? Well, looking at this, there's no base, right? So what does that mean if you see log? That means right here, there's a base of 10, okay? All right, so what you want to do is use what I taught you the other day is the inverse properties of logarithms. So we want to be able to rewrite 100, okay? And what base do we want to use? We want to use base 10, okay? So this is equivalent to log, and because the base isn't being written, it's base 10, and we want to rewrite the 100 so that it has a base of 10. So something like this, like 100 is, okay, 10 times 10 times 10 is 100, so that's 10 squared, okay? And we want to rewrite it with this base because then these are going to undo each other. They're going to cancel each other out. So if you have log base 10 of 10 to the second power, these are going to undo each other from the other day, okay? And the answer to this is 2. So log of 100 is the same as 2, okay? So how do we do something like this? Log base 3 of 1, okay? So the base is 3, so we're going to want to rewrite this, okay? Well, how do you rewrite 3 to a power and it be the same as 1? Okay, so this is how we're going to do it, all right? So we take log base 3 of 3, And what could I take 3 to still be 1? What power does this need to be to still be 1? Okay, well, if you remember from exponent rules that if we take x and raise it to the 0 power, that's always, always, always equal to 1. Okay, now there's one exception to this, and we don't really go into it in this class, but x cannot be 0. So 0 to the 0 power isn't 1, but any other number to the 0 power is 1. Okay, so we come back over here. Okay, what is this? So we could rewrite this as 3 to the 0, because 3 to the 0 is this value of 1 still, okay? But now we're going to be able to figure this out. So log base 3 of 3 to the 0, these are going to undo each other. What are you going to be left with? You're going to be left with 0, okay? All right, let me slide this over a little bit. Okay, how about this next one? Log base 3 of 27. Okay, so we want to rewrite 27 with base 3. Okay, so if you recall, okay, log base 3 of 27. Okay, so 27 is a multiple of 3, right? So it's 3 to the 3rd power. Okay, so 3 times 3 is 9, times 3 is 27. So 3 cubed is still 27. It's just another way of writing 27. And then that's going to allow us to know that this is going to undo. So log base 3 of 3 to the 3rd power, that's going to wind up being 3. Okay. Now this one right here, this next one, the natural log of 1 over e to the 8th. So it's ln right here. So the base that's not being written, that's right here, is e. Okay. So this is the natural log. There's a little e right here that we don't normally write. Okay. When you don't see it, it means e. When you see ln, okay. And we want to rewrite 1 over e to the 8th. Now we want to rewrite it so it's e to a power. We always want these to be the same so they undo each other. Well, how could you rewrite it? Well, if you recall that 1 over x to the a can be rewritten as x to the negative a. Okay? So 1 over e to the 8th could be rewritten as e to the negative 8. So this is going to go to negative 8. So we have natural log of e to the negative 8. These are going to undo each other. The answer is negative 8. Okay? All right, so this next one is log base 4 of 1 over 64. Okay? So we want to rewrite this log base 4. And I want to rewrite this as 4 to a power. So how am I going to do that? Okay, so 64. Okay, if you think about 64 is 4 times 4 is 16, and then 16 times 4, so well, 16 times 4 is also 64, right? So we can rewrite this as 1 over 4 to the 3rd power, because 4 times 4 is 16, and then 16 times 4 is 64. So this is still 1 over 64, but they don't undo each other yet, because it needs to be 4 to a power. Okay, well, again, we can use this idea of 1 over x to the a is equivalent to x to the negative a power. So this 1 over 4 cubed could be rewritten as 4 to the negative 3. So this is going to become log base 4 of 4 to the negative 3. And then these are going to undo each other because you have a base of 4 and log base 4 of each other. They're going to undo each other, the inverse properties. And what you're going to be left with is negative 3. Okay? And that's the answer to that one. So log base 4 of 1 over 64 is equivalent to negative 3. Okay? This is going to be some of the hardest ones right here. Okay? So how do you take a base that's 8 and get it down to a smaller number like 2? So when this happens, when you see the base is bigger than the numbers you have, you might be thinking, okay, we can take some type of root. Okay? So this is equivalent, okay, of log base 8. So we're taking log base 8 of 1/2. Okay, so we want to rewrite it so this has 8 in it somehow. Okay, so if you think about this, okay, the cube root of 8 is 2. So what we're going to do is we're going to rewrite this as 1 over the cube root of 8. Okay, now the cube root of 8. Okay, so what number could you cube to get 8? Well, it's 2, right? So the cube root of 8 is 2. This is still 1/2. It's just another way of writing it, okay? All right, so now we got our 8 that we need, okay? Because we need to have the same base, okay? Now, we got to remember that if you take the cube root, right? The cube root of x can be rewritten as x to the 1/3, okay? So we're going to start to rewrite this with exponents. So this becomes log base 8 of 1 over 8 to the 1/3 power. And now what we can do is use the negative exponent idea. And again, if you have 1 over x to the a, that's equivalent to x to the negative a. All right, so we're going to get this to become log base 8 of 8 to the negative 1/3 power. And now they're going to undo each other, and you're going to be left with negative 1/3. So log base 8 of 1/2 turns out to be the same as negative 1/3. Okay, let's look at this last two. Okay, so this one is log base 1/2 of 1 over 32. Okay, so I want this to be, I want to rewrite it so it's 1/2 raised to some power, because if I can rewrite 1 over 32 as 1/2 raised to a power, that's going to allow me to do the inverse properties, and the logarithm will undo the exponential, okay? So 32, okay? 32 is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power, okay? So this is equivalent to log base 1/2 of 1 over 2 to the 5th power. Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this is still 1 over 32, just written in a different way. Okay? Now, we don't want to rewrite this and bring it up like a negative exponent, right? Because we actually want this to be 1/2. We don't want to be 2 to a power. So we don't want to rewrite this as 2 to the negative 5th. That'd be a common mistake here, okay? Because we want this to be 1/2. Well, what is 1 to the 5th? Okay, so we can rewrite this as log base 1/2 of 1 to the 5th power, because 1 to the 5th is still 1, over 2 to the 5th. And then we can use exponent rules. Okay, so if we have something like this, x to the a over y to the a, that's equivalent to x over y raised to the a. That's one of those exponent rules that I wrote on the board for us. Okay, so this can be rewritten. This is log base 1/2 of, and because these are both 5, we can pull it out. So this is going to be 1 over 2 to the 5th power. Okay, so now we have log base 1/2 of 1/2 raised to the 5th power. These are going to undo each other, and you're going to be left with 5. Okay, so this last problem, okay, how do you undo, or how do you evaluate, not undo, how do you evaluate the natural log of 1 over the cube root of e to the 5th? Okay, now remember, what's not being written right here, the base, because this ln is base e. Okay, so how do you rewrite this? Because we want it to be e to a power. So let's start by doing that. Okay, so cube root of e to the 5th, that's equivalent to the natural log. I'm not going to write base e because we don't normally write it, okay? This could be written as natural log, and when it's ln, we know it's base e, of 1 over, okay? And the cube root of e to the 5th can be rewritten as e to the 5/3 power, okay? Now, what exponent rule we're using is if you have x to the a over b power, that's equivalent to the bth root of x to the a, okay? Or we could also write this as the b root of x raised to the a. But in this case, we have this one, right? So this allows us to write this as a fractional exponent, okay? Now, what we're also going to use, okay, because we're not quite ready to give the answer, is this needs to be rewritten as e to a power. Well, using this as we can use negative exponents to rewrite this, okay, because once again, we have 1 over x to the a. That could be written as x to the negative a. All right? So this is equivalent to the natural log of e to the negative 5/3 power. So there's a little e right here, base e. So these are going to undo each other again, and we're going to be left with negative 5/3. And that's the answer to this, okay? Now, for homework, what I want you to do, okay, is I want you to do worksheet ELF 3, and I'm assigning it today, March 19th, okay? So I hope you guys